All right, so I've been doing this SAT project. The first few installations, I've been reading SAT solvers. Off stream at one point, I wrote a little CDCL solver. It's not very sophisticated at all. And so one of the things I do want to do is to build this up to the point that it's more carefully designed. The I might not try to do the absolute most that I could do to push its performance at the lowest level. I might go for that. I'm not sure. But right now, I haven't done anything like that. Like, I'm just using fat linked lists and really uncarefully thought out data structures. And I've learned a few things on how to just speed this up from the data structure low level. And I've also learned, reading the mini SAT over the last couple of sessions, I learned how to use a better data structure algorithm at the high level that really streamlines a couple of the stages of the CDCL solver, which is what this kind of solver is. So we could be going down that road at some point, but I was thinking that today, and this is what I put in the title of the stream, I think that today what I'm more in the mood for is to work on the other half of this problem. So the CNF comes in, and I'm going to have to draw some pictures of like what the CNF is and what the difference is between that and the thing we actually want to use as the input interface. But right now we have the CNF comes in and we can solve it. Let me actually set us up to build this project. Right, if I run this, no, I need the run function to be on FAT-SAT. Okay. There we go. So if we run FAT-SAT, we get this. Let me show you the FAT-SAT test, just to get us absolutely started here. Sort of what I need to do today is to audit what I have, draw pictures mentally, verbally, of the and visually of the way the SAT to CNF conversion works, and then try to implement that. Those are kind of my goals. So once we've done the audit, we'll be prepared for how to fit this in if it's another part of the library, if it's completely unrelated. We'll get some ideas about that by the audit, and then obviously depending on how complex the transforms will need to be when we put them into code. So what we have here is I set up a little test formula. Here we go. I print out in the log using this formula here. Why does it print out using formula so many times? Probably because it can learn along the way. So yeah, let's try to figure out how my log works. Using formula, string from CNF. So at the beginning of, okay, this is just at the beginning of each loop, it shows the formula. So if I were to learn a clause, it would become visible there. So using this formula, we make a guess for a value. We guess that x0 needs to be -1. Then we propagate. And we guess another value. Propagate value happens in this loop here, where we are, so if we guess that x1 is false, or x0 is false, we would then learn, so we see here, like, if x0 is false, then x1 has to be false, because that way that makes this clause true. X3 has to be false, x5 has to be false. That makes sense. It then has made all of the deductions it can find, because it can't deduce anything from these since they're falses and because there are two variables, and it can't deduce anything from these because they're falses. So yeah, then it makes a guess of x2 being 1, and so that satisfies this. Okay, this is interesting. x0 was false, so this was already true and didn't matter. Yeah, this one becomes true now, and yeah, so it makes a couple more guesses. It just happens to be that in this case the heuristic led to nothing but good guesses and it finds an answer. So this appears to work. What we don't have in this log is any picture of the conflict propagation. Let me see if I can figure out how I would adjust this to trigger a conflict resolution, I mean. So it's guessing that x0 is going to be false. And that works. If I could make it so that x0 could not be false, how would I do that? Well, for this to be false, makes this false. So then x2 has to be true. So if I wanted to make it so that x0 had to be true for this to work, but that it would guess false, how would I do that? I had a better example than this before, but it looks like I didn't keep it. Okay. This becomes false. Let's take out this, or rather, let's make that. So now this x0 here doesn't have a negation on it, and so it's going to guess x0 is true. X0 is still, by the heuristic, x0 is still the one it wants to figure out first because it's so common, but true is more common than false, so it's going with x0 true. And then it's going, okay. We can't deduce anything from that because, well, I can't. It should have been able to deduce the not x4 right here. What am I missing? Make a guess. Oh, that's fine. Yeah, so it makes a guess at the end of the loop, and then it comes up here, prints its formula again, and then does the propagation. So it does do the propagation at the right time. The order on the log there's a little funny. I think we could say like, start by logging the formula, and then let's only update the log of the formula if we attach a new clause. So that would make the log look like this. Using this formula, it guesses the value x0 is true. It propagates that x4 must be true because that's the only way to make this clause satisfied. It guesses x1 is true, which handles both of these. Yeah, so this setup doesn't do what the other one does. What was the setup I had that made this work? Let me just sketch it out. It was like this, and then let me give this space so that if I want to line them up, it'll work. So any of them can be true, and then we say so if this was false and this was false, this would have to be true. So then let's put in another one that puts it in the opposite situation. So if this is false and this is false, then this would be impossible, right? And then we say, look, you can't have, if this is false and this is false, this works, but if this is, right, so the really direct way to do it is to say like something like this. So this is false, which would force, since this part x0 would be false, then we would need this expression not x1 to be true, so we'd make x1 false, which would do this, but then we'd run into this, right? That would create a conflict. But if we keep that and we compare it to the run we have, yeah, this should work, except that might be the difference. Yeah, okay. that a false, make that a true. Okay, so the idea here is that these three are gonna force this to be false, because if this is true, then you can like imagine this part gets eliminated. The rest of this is impossible to satisfy. We can't have this be false for this clause, this be false for this clause, and then still satisfy this. So this part here, there's no way to set the variables 1 and 2 in order to satisfy all of these clauses. So x0 has to be false to get the job done. But at a single glance, you would think that x0 should be true because there are more truths in the problem than falses. So that should lead us to a guess that creates a conflict. x0 we guess to be true. x1 we guess to be, or we propagate that to be false. So since x0 is true, this is already, this expression here comes out false. So we need this one to come out true. So we set x1 to false. And then we go, okay, so if we have that this is coming out false and this is coming out false, then x2 needs to come out true. But then we have a conflict on this clause. They're all coming out false. So then it runs the resolution rules and it figures out that x0 needs to be false. That's what it comes down to. We have better ways of running the resolve now, but the way this one runs is it takes this clause and it goes, okay, if this clause compares with this one, the negative x0s are redundant, so when we resolve them, we keep that. The x1 here and the x1 there is redundant. We didn't keep that. We kept the negative x2. Which one did we? We must have compared this clause with this clause. This was redundant, so we kept it. These were opposites, so we removed them, and this was unique, so we kept it. And then that must have compared with this one, and there the opposites are x2 and not x2, so we get x1, which is unique, and the x0, which is redundant. And then we take that clause and we compare it to this one again, and we get this as the final one that we boiled all the way down. So then we put that in there. We backtrack to before, and we propagate x0 equals negative 1. We propagate that because it's required by this clause, which then propagates all this information, and then the last two guesses gets the job done. Because once x0 is false, these all just click into place. And then these become irrelevant. They can be anything. Yeah, okay. So there's how the algorithm works. There's it working at least. There's definitely a lot we could do to make it more efficient based on what we learned from mini-SAT's way of tightening up some of these things. The resolution doesn't need to be this complex, and the propagation can actually be a little better too if we accept a more complicated data structure for accelerating the machinery on that. Okay, so that part makes sense, and you can see the way I specify this to it is through this like CNF formula clause F. So I have like these lists. I say like here are three here tells it there are 3 literals in the clause, and then it's like the negative of 0, 1, and 2, the negative of 0, 1, and the negative of 2, the negative of 0, and the negative of 1, and so on, right? But that's the only way I can specify these things, and that's not super interesting. This is the CNF form. So what I want to do today is to be able to specify a SAT form. So let's do a little bit of like imagination what that would be like if I could do a formula directly. So what would happen is I would have something like, I don't know what it would be called. We'd call it just do we want to call it an operator or there are conjunctions and disjunctions, but what are they? They're just operators, I guess, or they're like sub clauses. They're terms. What do they call these? Let's look up what the literature on this topic calls these. Gate. Okay, they call them gates. I'll go with that. So it would be like this. Right, we'd be like G1 is G0, G1. All right, it could look like this. Right, so there's an option. It's a little bit too verbose for my taste. Like, I'm going to have a hard time specifying this. Let me show you the kind of problem we would want to be able to specify. Say I've got an interest in creating a SAT solver for Sudoku. All right, that'll be our case. So we'll go I equals 1 to 9 to look at all of the different parts of a cell, and we'll go like I'm trying to think of the easiest way to do this. So I'm thinking like we have like a clause, I guess I just don't want to call it a clause because that's in the conjunctive normal form terminology. So we call it an expression, maybe. Let's see if we use that kind of terminology. And then we go, all right, give me, so that's just an expression empty, right? And then we would do, or like nil. And then we would do or on the formula between this expression and a variable that we get. So this would be like FAT-SAT expr variable maybe. Right, so we'd be like variable 1, variable 2. We could do a list from 0 to 8 instead of 1 to 9. So that our 8 variables come out and we OR them all together into that expression, and then we set that there. So the nil expression, when you OR that with something else, would just give you the something else. That's what the nil would be for. So if you want to make a chain of ORs, you'd start with nil and accumulate onto this. If you want to make a chain of ANDs, So this is another thing we would have to do. This would be our at least one constraint. And then we could call these constraints, right? Instead of expression, we would be like constraint. Makes it verbose again, but I like the name. I just wish I could make it short. Like I could just call them con, right? Short for constraint. Constraint or. So that means we need at least one of them. And this is not. This is at most one, right? So this is the one that will construct, that will represent the fact that you cannot have two numbers in the same cell. So we have to loop over all pairs of numbers now. So this was a loop over each of the possible numbers that could go into a cell. This is a loop over all the pairs of distinct numbers that could go into the cell. So we get like 0 and 1, 0 and 2, 0 and 3, 0 and 4, da 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 da, 1 and 2, 1 and 3, 1 and 4. We don't care about getting the pairs both ways. So that's why the second one gets pushed in like this. And then should be con. So we get the variable constraint pointers for I and j, and then we go at most 1 equals FAT-SAT con and into the formula at most 1. This will be VI and VJ. And then we'll need an expression here, which is you can't have, it's the not of this and this, right? So not this or not this, right? So in other words, we're saying not VI and VJ, right? Which is going to turn into not VI or not VJ if I want to do it as an or. But I could do it either way, right? So what I could do here is say like, okay, we want a FAT-SAT con both is the con and of VI and VJ. And this is not both, is FAT-SAT con not of both. And so then we put not both in, and we're anding together all of the not boths that we can generate. And then at the end we get the cell rule is the FAT-SAT con and of at least 1 and at most 1. And we could set something like there's our formula root, and now we're done. Now we are not building the formula anymore, right? We could also say like this is not the formula, but this is the formula builder. Con builder. There we go. Okay. This is like con begin, con builder, and then we can have like build the formula, and then there's convert the formula would be like we go FAT, SAT, CNF formula, constraints, convert to CNF formula, formula equals FAT, SAT, so right, this would become CNF formula from con, right? You give it the arena you want the formula to live on and the constraint builder. So you begin this here, you fill it in. Instead of setting a root, you could also just say, at this point we pass in, because the root is only relevant in the sense that it tells us this, the formula builder, or the constraint builder, is now more so carrying the allocation burden and the deduplication of things like, okay, if we see the same variable twice, what do we do, right? So if we keep on going, so this is how to deal with one cell. And what we want to do, I think, is just build the whole thing today. That'll be fun. So we need a loop up here that'll be like going over the grid of a Sudoku grid, right? So it's going to visit each cell. And now each cell contains 9 variables. So we're at the cell we're at is 9 times the cell, the base cell index is 9 times x plus 9 times y, right? So this is at the highest, each row is 9 cells, starts 9 cells later than the previous one. So if we increment y by 1, it's like going 9 cells forward. And if we increment x by 1, it's like going 1 cell forward. And each cell has 9 variables. So that's how we get our cell index. And then at the bottom there, we say we want at least 1 for each cell. We want at most 1 for each cell. So this ensures we get exactly 1 variable for each cell. And we put those together. That makes our cell rule. But I think what we could do here is say that we have a sort of root one, which is going to start at nil, and it's just going to gather up all of these. So this would be like root equals fat sat con and con root at least 1. And then and in again at most 1. So the at least 1 and the at most 1 both go into the and that's what each cell has to say. What does each row have to say? Well, we visit rows by going on a loop across the y values. The row index can just be this. And then we want to think about each number, right? From 0 to 9. Or from 0 to 8 or 1 to 9, right? We want to think about each possible number in the game. And we want to think about, for each number, the rule is, like if I'm thinking about the number 1, there should be at least 1 1 in the row, and there should be at most 1 1 in the row, right? If we had at least 1 1 and at most 1 1, then we have exactly 1 1, and then we've done it correctly. So the at least 1 rule, we don't want to loop over i's anymore. What we want to loop over is x's, because we're going across a row. So we look at each cell and we say, okay, each of you is starting from the row index plus 9 times x. That gives us the cell index, right? Cell index is going to be the row index plus 9 times x. And then the I is telling us which number we're thinking about. So we increment that. We put that in with a stride of like 1. There's no multiplier on it. So that tells us which variable to grab, which is the variable that tells us on this cell, which is based on this x and this y. Give me the variable for the number I. And we're going to OR together everything across this row. So there's an OR on the 1 for the first cell, and the 1 for the second cell, and the 1 for the third cell, and the 1 for the fourth cell. Similarly, there's an OR for the 2 of the second cell, and the 2 of the third cell, and the 2 of the first cell, and so on, right? They all get ORed together by row. And then we do the same thing here, which is we look over x, and I'll have xx to be the second x variable. And we're looking at 2 different cell indexes here. Cell index x. Right, so we have 2 different x positions on the row, and we get 2 different cell indexes. So we grab a variable for both of those, and we say, here's the expression for both of them, here's the expression for not both of them. And we put those together into this list. Then we take both of those rules and stick them onto our root. So that's the row rule. The column rule now. So in the column rule, we'll look across x's, and then we'll look across variables, and we'll look down the column by iterating y. And so then we can get our row index by going like this. This becomes this. This becomes this. This becomes, so now we have 2 spots going down the column at a time. This is like this. Put them together, take the negation, and then throw that all in there. So column rules, similar again. All right, finally we have to do the boxes. Now this is going to end up feeling a little different. So we have box x equals 0 to 3. and then box Y does the same thing. And that tells us, these two together tell us which box we're in. I could do this like this, right? That should be fine. So I'm iterating across a grid of 3, 0, but I'm striding by 3. And the reason I'm doing that is because now I still want to do an at least one and an at most one, like I have been doing. So that'll go there. Let's get rid of the one below the stand-in. So the at least one is going to be another double loop, because we're looking over x's and y's. So instead of the box versions, we're doing this and this. Let's do it like this. Box x plus 3, box y plus 3. So we're looking at x is touching the correct state cell positions. X and y are going to the correct cell positions. And then we're saying at least one of those has to have. And right, we also need that loop by number in there. So that's like that. So we have the loop by box right here, the loop by number right here. And then we loop inside the box here to build the at least one. And we're going to have a similar loop inside the box here. Oh, this gets even weirder, doesn't it? How do you do a loop inside the box inside a loop inside the box? So I think what I should do, I'm going to change up the plan just slightly here. I'm going to make this looks like a loop over 9 spots directly. And then I'm going to pull out the box x and y coordinates that I would get from the spelled out loop like this. Modulo 3 divided by 3. Okay, so I still have box x and box y, but they're being derived from a singular loop like that. And then what I can do is I can go apply the same logic here. So instead of x and y, I'll be doing, let's see, let's call it something like k, something that doesn't collide with any of the other things I'm using. Yeah, I'll go with it. And then pull the x and the y out of k using that rule. And then right, and then cell index is computed from one of these things. So we've got an x and a y by going box x plus box y plus, right? And then cell index there, boom, boom. And then the at most one part is going to be like, what if we took k and a second k iterator, and then pull out 2 cell locations from that. And then finally, like this, cell index k, cell index kk, there we go. So now we have a loop going through the 9 spots of the box, and another loop going through the pairs of 9 spots in the box. and we build the at least one and at most one and put those into the thing. So there's still the same number of them as there should be. They have to be arranged a little differently in order to relate the cells in the box correctly to each other. Okay, so the the plan then to get started is we need to have the API that actually builds this, and then we need to talk about, like, we need the API that is being pretend used by this Sudoku The Sudoku rules here are all built in terms of this constraint builder. This is then it starts like that. And so this is then the conversion algorithm. And we'll talk about that second. So let's get this constraint builder sketched out. It's going to need an arena. And for now, I think that's all it'll be. It might make sense later on to do some work to notice duplicates. But I think, yeah, we do want to watch for the maximum variable. I want that much at least. Now, the constraint we're going to need an enum because there's a couple different constraint kinds. There's going to need to be a way to tell them apart. So it can be a variable, it can be an and, it can be an or, it can be a not, right? Not really any use of a union here. Yeah, that should be good. And I guess we also want a special nil one. And the nil one won't be valid as a constraint. So basically, if I gave you a formula and you actually could walk through that formula and find a nil, that would mean it was built incorrectly, but it is a useful atom to pass through the construction functions themselves to make the API work better. So let's look at what functions we need. Constraint builder functions will include beginning the construction of the constraints, man, my fingers are in the wrong spot. I keep hitting it. Give me 1 sec. Okay, so we want a nil, and I will just have it take the constraint builder. It's kind of funny that I called this the con, but it's actually the thing that is not the con. Okay, builder. So there's nil. You can ask for a variable, and for that you just put in the index. You can do any of the logical gates, right? So and or not. And maybe later we would want to add others, but that's like enough to get you started. And then there's the construction of the CNF formula from that, which is for a little later. So that's FAT-SAT CNF formula from con. That takes the constraint builder and the root constraint you want to build with there. Okay. So let's fill in all the easy ones, and then we'll have a dummy in place for the CNF formula where the interesting stuff has to happen. So these easy ones are just like, you know, we're setting up the little construction helper by putting it onto our arena here. It wants to know about what arena is using it, or it is using really. It wants to know which arena it lives as a stand-in for the arena for the rest of these. It carries the arena through. It becomes the allocation manager for the whole subsection of the API, so it carries the arena that it allocates on. And that can be risky. I should double check that I'm not putting that on. Yeah, okay, good. Not putting that on to a scratch. It might looking at that, I'm thinking that might not be necessary. The API is clean enough that if I were to explicitly parameterize the allocator rather than bundle it, I could put this on a scratch, and that seems like what I would want in the long run. Right, I could go like scratch arena. I wouldn't need that at all. Or I would, because I still want to allocate it. But it would be like, you don't set that, you just return on it. There we go. So this can be like arena temp scratch, arena get scratch, arena release scratch, and then all these things which take the BLDR first need to become things which take the scratch arena first and then the BLDR, with the exception of the ones called nil. Those can just not take an arena because there's nothing to allocate there. I mean, in theory, what we should really be doing here is just saying there's no such thing as this. Instead, there's just a global variable here. That looks like that. And so whenever you want the nil, you don't call a function for it, you literally just take it. There never needs to be more than one of those across the program. Okay. And then we can get rid of this and start by implementing this. So for variable, what you do is you are going to create one of these. You give it the kind variable. You give it the, let's see, variable index, and then you return it. You're done. For and, you give it the and type, and you give it a C0 and a C1. For or, it's the same thing. So there's a not. But this is only part of the story. What if one or both of these is nil? That's the other thing, right? So nils are never supposed to show up here, but they're allowed to be passed in here. And when they get passed in there, they are being used to simplify the construction process. So we want to think about what that would mean. If C0 is a nil, then we would just return C1. And if C1 is a nil, we would just return C0. So this now becomes a little bit more like this. If C0 kind equals nil, then the thing we return is C1. Now, if they're both nil, this will return a nil, and that's fine. We didn't construct a new nil. We returned a nil, and that nil can go on and get passed into something else. As long as the nil isn't the final root, it's still fine to return it, right? Because it'll eventually get incorporated into something that isn't nil, and the nils get removed. The only way there's a problem is if somehow, as long as we don't attach nil in the leaves of the tree, then the only way for there to be a problem is if the root itself turns out nil somehow. But if we made a correct construction, that just wouldn't make any sense. It shouldn't happen. So it ends up looking like this, right? If you put a nil in either spot, then the other one comes out by itself unchanged. So like if I say, hey, what's the and of this variable and nil? Well, the point of nil is to say that we can start off with something being nil and then make a chain of ands or ors iteratively on that thing. And so if you put a nil in as one of the two sides of an and, then you just are saying nil and this means that other thing, right? Now what's funny about nils is it's going to do the same thing with or. Nil isn't acting like false here, right? So it's not like a thing where, if one of these was nil, the whole thing has to be nil because it's an and if you're thinking like Lua or JavaScript style thinking, it's like, oh, null and something else or nil and something else should be false. That's not what I'm saying. I'm saying no information, an empty constraint and an actual constraint. Well, the empty constraint we'll say is always satisfied when it's included inside of an and. That way we can make chains of ands by starting with nil and then anding those iteratively. And if we only do one step, then we just get the variable. If we do two steps, we get a single and. If we do three steps, we get an and another and, right? We sort of use the nil to let the API work correctly, not to form a certain kind of logic about what nil ands and ors to in other cases, if that makes sense. Hello, Raiders. All right, so this one is the or case of the same thing. If one of them is nil, we take the other one. This one is a little simpler. Rayzelma, hi. How are you doing? Thanks for the raid. The SAT solvers, I haven't touched it in a week, but it's going all right. I'm kind of getting into the fun stuff here. I'm working on the quintessential SAT solver test case, which is my Sudoku rules today. So that means I've got to build the API that lets me construct the formulas more freely. What's the problem here? Oh, else if. Yep, today I'm not studying mini-SAT. I'm building up on my SAT solver based on what I learned from mini-SAT and other little SAT things I've learned. Although what we're doing today is actually not something you can find in the SAT solvers themselves. The SAT solvers, they solve the problem once you've turned it into a so-called CNF. So really what I'm doing today is the other side of the problem, where you take a standard Boolean formula and convert it into CNF. So I have to do the API for constructing my Boolean formula and then the conversion to the CNF so that I can send data that is sort of constructed in a human in a human interface way, which is understandable Boolean formulas, to the solver, right? I'm kind of building the pipeline that takes my inputs into the solver today. And that isn't something that Mini-SAT or anything else showed. And I haven't really showed how I haven't showed how those algorithms work yet, but we're getting there soon. And yeah, that would become the formula to solve. Yep, and so the formula builder for now is a fake. You'll do the real one later. Okay. Yeah, so now you can see when I run it, I just get an empty formula because even though I've built this presumably, this drops out as just an empty formula still. But if I did everything else correctly, then in theory I have a formula here. So let's do a stringize for the constraint. This is going to be really hard to read, and I'm trying to think of how to dump it in a way that's going to be close to readable. It's going to just be a very deep tree. So like if I had a shallow tree, I could just do this, right? You'd be like, oh, here's an and the and contains an and, the and contains an and of x0 and x1, and it contains an and of x2, and it contains, so you know, this one, these two go to that, this one goes to this, and then this contains an or of not x1, not x2, right, and so on. Like this kind of works, but imagine there's like a chain of, what is it going to be? It's like 9, 81, 720 of these deep or something like that. It's too much. Now if I have an and of x1 and x2 and x3 and x4, I could just print that as this, right? So the idea there being, if I have children whose Boolean gate, if I'm an and my child has a Boolean gate and, I don't need to do an indent and I don't need to reprint the and for that. I can just treat its children as my children directly. So how would an algorithm for that look? Say I had this and I had and x4, x5, right? It would come here, it would say, okay, I'm an and, oh, my child's an and, so iterate it without indenting. It would go like, okay, I'm an and, print and, oh, I have an and child, so iterate it in a special way where I don't increase the indent, and I don't print the and at the beginning. So it goes, okay? So just looking at the children silently. We go x1. Oh, and we have an and since the parent is an and, x2, x3, right, okay. Okay, so that's got to happen. Let's see how good it looks if I just do that. So that's going to mean that in addition to the usual thing you do, which is to pass the indent through, you're also going to pass through the show operator control flag. And we could say that is like that, and this is the base one, so this can look like this, and it just calls to the underlying one. Which looks like this initially, and then it's going to go into this one, and it'll go, okay, if I need to show my operator, then we switch on what kind we have here. Cool, cool, cool. And let's see. Those ones are simple. If it's a variable, we just print out x and the variable index. And if it's a nil, we just print out nil. Okay, so that's what happens if we show the operator. Well, I'll change it up a little bit. If we look at a variable, we want to print that even if we're not showing the operator, right? So this is more like this. And then indent plus equals 1. Here I want to put the indentation in. One, 2, 3, 4, 8, 16. Here, we'll make each of these a block of 16 and go like this. Now we'll make each of them a block of 32. We'll take a couple of them. The reason I'm going so deep on the indent string on this one is because, like I said, I expect these to be big trees. It might be conceivable that we get trees that indent all like, you know, way in like this and still not consider that a problem. So 64 spaces might not even be enough for some problems, but seems like a pretty good number at the point where you get past 64. If you're still wanting more fidelity, you might already be at the point where you need a better visualization plan than this anyways. So that seems like a good upper bound to me. And then you put the thing down. If you showed an operator, then you indent and you look at your children. So string eyes recursive, arena, con C0, show your operator, yes. In here, use this indent level, out. So this is the basic one where we always would show the operator. But then what we want to do is say, okay, how do we know when to not show the operator? And the answer is if we look into C0 and we see something that has another and, we set the show operator to false. So So if the thing underneath us is not an and, then we show the operator. And then same thing again, but with ors here. With nots, we don't do this because if we have a not of a not, that is just fine. We just print that out. I mean, ideally what we would do is we would eliminate the whole chain of knots, get it down to just 1 or 0 knots. That's a little bit outside of what I know how to do easily here during the print pass. Like I'd have to look at the knot and say, well, okay. We're always going to show the knot if we arrive at it. But what we'll do is we'll say count knot chain, right? So we have 1 here for the knot we started on. Then what we're going to do is we're going to say do a loop which starts from con C0. So this is the first child here, and continues for as long as this is still a knot. So if we look ahead by 1 and we find a knot, then we continue. And we iterate forward by looking through that chain of knots. So if we got to this increment, then we know that this was already a knot. So this is another valid child, and it's the only child. And we increment our count. If at the end, the count knot chain has an odd number, then we would print the knot and whatever comes after it, right? We would want to have maybe we want to have this look like this. So the C starts by looking ahead by 1 and continues counting up however many knots it finds until it finds something that's not a knot. And that's the one we're going to show next. So this skips over all of the knots and tells us which one to show next. And it tells us whether or not to print a knot or to just hide them all, depending on if it's an odd or even number in the chain. Okay, so we wrote our stringizer, but let's make sure to use it. So we build our string here, log the constraint. That's going to be like this, string8 list conster list, something like that, equals empty FAT-SAT string from con scratch arena. Here's the root constraint we're interested in. Start with an indent level of 0 and give us a con string list. We're going to join that list together into a single string with no gluing characters, just all one big string. And then we'll write that out. Okay, this looks a little wild. Not quite, not quite what I would expect to see. Some of it looks structured correctly, but something's off. Indent nil con indent plus equals 1. Only if we're showing the operator. There's no path here where we don't new line. Well, I guess there's a path here where we don't new line. So the only time we don't new line is when we don't print something. Let's just use the debugger. Let's see, wrong project. Let's open the CNF-SAT project. Step into there. We want to see if this part makes sense. So let's look at the con we're seeing. Okay, it's an and. The indent of 0 means nothing should get printed. It's showing its op, so it should do that, and the indent should go to 1. Then it should look ahead and go, okay, C0. Oh, look, this is saying C0 as well, so that's one mistake. This should be looking at con C1. Okay. Get us again this far. Okay. So are we showing the operator? No. And then we come in here, the indent level is 1. You look at the and, we're not showing the operator. And it contains an and for its first child, so it's not going to show the operator on that one either. So we're still at an indent level of 1. And the and contains more ands, so we go in again. And this and contains an and, so we go in again. And this and contains an and, so we go in again. This is not surprising. This is why I wanted to think about how to eliminate these, but I am going to look ahead to see how far this goes before something else happens. Right, this whole thing is a long chain of ands, right? And each of the C1s hanging off of it is something else, but there's this long, long, long chain of ands that's being treated all as one big thing here. So that makes sense. That makes sense because we and everything together into the main formula. What I want to see is, when's the first time we reach anything that's not an and then? Okay, so we reached an or. And so the indent level here is going to become 2, because if this is an or, then in the previous step, you can see how deep our recursive function is running. We might want to avoid doing it this way, because that's a pretty tall call stack, and as much as I like the simplicity of a recursive function, it makes me nervous when it gets that deep. And basically, every cell generates 2 and, so there's 81 from that. Every row generates 2 every row generates 2 ands. Another thing that's happening here is that some of the chains of ands are themselves ands, which are going to get flattened out. Like, all of the ands are getting flattened out in one go, even though there's sort of a hierarchy in my mind of which ones are different. They're not, the hierarchy in my mind isn't actually going to be preserved by this flattening process. But anyway, so we're going inside the or, and this is going to be a chain of 9 ors probably, is my guess. Because that's where we're using, yeah, okay. So that's making sense. Eventually we're going to get to a point where it's not an or anymore. And so we see variable 0. So the indent here was 2. Now, I guess my question is, what if we put out onto the string so far? We've put out a bunch of these. Okay, I see the problem. The problem is that I'm indenting all the time. but I'm not always actually printing something at every level. What I want to do is I need to wait on this until I know that I am printing something. It's probably going to have to look like this. I mean, the other thing I could do is keep the indent rule living in its own separate node like that. So it goes, if you're going to print something, then you indent, you print, and you new line all at once every time. Okay, so just dumping this took it a while, but you can see now we've got, okay, x0, x1 through x8 are all happening. So these are the 9 values of the first cell. One of those has to be true. It cannot be the case that it is x0 and x1. It cannot be the case that it is x0 and x2, and so on 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 and so on. So we have, you know, the triangle number of 9 of these, essentially, right? We have 9 choose 2 of them, which is going to be, you know, 36 or something like that. So we get 36 of these, then we get an OR of these 9 things. So why 81, 82, 83, 84, 85, 86, 87, 88, and 89? I'm not as sure why those ones. Probably because we're looping by a Y before we loop by an X. Like we have, yeah, the Y is deeper here. If I switch that around, then you would be going across first and then down second. That would make it look like this. So we get 36 of these. The first one is the same, and then, yep, here's the second cell. One of those values has to show up. So these are all the things we call the cells. Each OR here. So there's a cell 1, cell 2, cell 3, cell 4, cell 5, cell 6, cell 7, cell 8, cell 9. There are 81 cells. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81. Okay, there's all the cells. So after that set of ands, or nots here, we'll finally get something new. And yes, it's just another OR, but this is the OR that goes across a row. Right? We're building up rows now. So we start at row 0, or the first row, and we look at x0. Well, that's the number 1 inside the first cell. This is the number 1 inside the second cell. This is the number 1 inside the third cell, and so on, right? So we have a constraint here saying, well, we need to put a 1 somewhere in the first row. Now, here's the other question I want to ask. How big is this file? Okay, so 49,000 lines. It's 49,000 lines long just to see the entire set of Boolean logic, like the entire Boolean logic expression after I've hidden away a bunch of like chains of ands and ors into single lines. Really, this here, it looks like 9 variables inside of an or, but really what it is 9 variables inside of 8 ors, right? We've hidden that part. So there's a lot. It's a big data structure that captures the whole basic thing. So it will possibly be a difficult benchmark. Like, it might be that my thing is way too slow to actually solve this today. But let's let's talk now about the cool thing is the reason I wanted to do all that and can take a look at the log there was to confirm that it did construct the thing which I imagined it was constructing, which it looks like it did. So what we've done is we've confirmed that the builder part works. Now we have to convert that to a CNF formula. So this is the part of the stream where I'm going to switch over to drawing for a little bit, and we'll talk about how conversion to CNF is going to work, or rather how it can work. There's a couple of algorithms, and I think it'll be fun for me to have a chance to go through them before I try to implement any of them. So we want Milton here. There we go. So, yep, that's ready to go. Let's come over here. This is where we're going to talk about. Over here we have mini SAT notes. Now over here we're going to have let me dust off the tablet a little bit. Over here we're going to have the SAT to CNF nodes. Okay. So let's talk about, first of all, what do we have? The definition of a SAT, right, versus the definition of a CNF SAT. So a SAT formula can have ands, which we can write like this, and ors, which we can write like this, and nots, which we can write like this. Right, this is like that and that or that. This is like not that. So I'm kind of showing this. These are binaries, and this is unary, and these can be freely combined as expressions or gates, etc. Right? We can put them together somehow, something like that. That makes a SAT formula. The CNF form is a subset of that. Oops. And it requires that we go like this. We can have and on top, or below and not below or. So example of what a SAT can look like is like something dot or that or not that and that or not that or not that and that and da 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 da, right? So all of the ands are at the top level of the expression, and the ors sit underneath the ands, and the nots sit underneath the ors, right? We don't have not outside of one of these things, and we don't have not at the top level between and across ands or anything like that. They're just all the way down there on the variables. Then we have ors combining the positive and negative versions of variables together, and we have ands joining those together. So these right here are called literals in this form. These right here are called clauses in this form. Right? So if I were to circle, just to clarify, the building blocks are the same, but this is the main rule describing SAT. In other words, you can put them together freely as expressions, whereas this is the main rule describing CNF-SAT. And this here is an example of a CNF. If I wanted to, I could give you an example of a non-CNF, which could look like taking inspiration from our Sudoku rules. The Sudoku rules look like this. Right? So that's just, freely specified Boolean formula for the SAT problem. This is the conjunctive normal form for the CNF-SAT formula version. Okay? And our goal is to convert from this to this so that we don't change the problem in a meaningful way. So we were trying to originally ask, how do you satisfy this formula if it's possible to do so? And if it's not possible to do so, just let me know that it's not possible. And now we're going to convert that to a CNF-SAT, but we still want to be able to ask the same questions. One, how do I solve the original problem, the unconverted problem? And make sure that the solutions that were valid here don't change. It shouldn't be possible to solve it in this formula if it wasn't possible to solve it in this formula, right? So the meaning shouldn't change. And the solutions that we get from this should somehow correspond to the solutions we could have gotten over here, right? And similarly, if this was unsolvable, this should remain unsolvable. They should match up with each other and have that kind of equivalence. So there's two ways that I have found that are pretty easy to think about to do this. One is the naive conversion. In the naive conversion, we're going to call, it has the property of equivalence. So by equivalence, we mean same set of variables evaluates to true under the same conditions and evals to false under the same conditions. In other words, you could swap out these two formulas. If two formulas are equivalent, then they have the same set of variables, and if I evaluate one formula, it's the same result if I evaluate the other formula given the same variable states, right? So if I set all my variables a certain way and I look at one formula, it'll either say true or false. Then all of the same variable states can be transferred to the other formula and it'll say the exact same thing the first one did. So they might not be the same internal contents, but they have equivalence, which means they have the same set of variables and they evaluate to the same things. Another way to write this would be for all models. So let's say that M and N are these things called models over our variable set, V. I don't need two models. I don't know why I did that. For all models over our variable set V, our first formula evaluated at M is equal to our second formula evaluated at M is the same thing, right? This is being the equivalent of saying that formula 1 is equivalent to formula 2. Okay? So we're saying that this is terminology equivalence. This fancy way of saying if I loop over all of the models that are possible, they will agree on every single one. Okay? So that's equivalence, and that's what the naive conversion is going to produce, is an equivalent formula. It also has the property of exponential size increase, and this is a big downside to doing things this way. So we'll see why that happens when I explain how we do it. So the idea is let's build a function I'm going to use some color to keep this readable as I go, called CNF. That will take in a SAT formula and produce a CNF-SAT formula that is equivalent. So, in other words, if we have formula 1 is a SAT formula over the variable set V, and then we say, whoops, I've lost my, there we go. And then we say let formula 2 be equal to the CNF function output when we put in formula 1. So what's happening here is we're saying CNF is a function, it's going to run on formula 1, and it's going to produce formula 2. Then, if that's true, then we'll be able to conclude a few things. If this is true, then this is a CNF-SAT formula over the set of variables V, and we can conclude that formula 1 is equivalent to formula 2. Okay? So this is a more technical step-by-step explanation of how CNF is defined. Here's the English definition of CNF. Here is our dream for CNF's properties more technically. If we start with, if we have this and we have this, then we want this, right? We want a guarantee that this is a CNF formula, not a regular SAT formula freely, but a specific CNF one, and that they're equivalent. Now, the way it works is going to be like this. We're going to start thinking about how we will take in different partial SAT formulas, different patterns of a SAT formula, and think about how we would convert those to a CNF-SAT formula. So, So if we have the CNF function, and it takes in, let's use orange for these things. So if it takes in something like true, just a fixed trueness, well, that can come out as a fixed trueness, right? Similarly, if we had CNF take in a fixed falseness, oops, that's going to equal falseness. And what I mean by taking in trueness or falseness, what I'm saying is, like, while we didn't really spell it out, a formula could just be the constant true, if you wanted to think about it that way, right? We don't usually bother with having the ability to specify constants in these things because they don't serve any useful purpose. They're so easy to eliminate that we don't even bother putting them in. But you could imagine a formula that's just always true and has no variables, or always false and has no variables. Okay? So that's one nice thing, is that those both count as CNF formulas by themselves. Because they're just literal, so it's a literal with no use of any of the outer things, but you can think of that as a single clause with a constant in it, or something like that. Now, what if we took in a CNF formula, or we took in a formula that was just a variable, right? So we'll just say this is like variable. It's not a specific variable, but it's a node that is a variable, right? We're thinking of it in terms of those nodes that we use for building expression trees. Well, the CNF version of just a variable is actually just that variable again, right? We don't need to do anything else to it. So that part works just fine. Now, the next pieces get a little more interesting. What happens if I take in, and let's think this through, what happens if I take in the not of, well, what can come under a not in a SAT formula is anything, right? So this can just be a formula now. I'll give it a symbol like that. And I'll underline it to specify. The underline means that this isn't a specific thing, it's a placeholder, a pattern matcher. So not on any formula. Well, we have to be a little careful here. If I just write that this is going to be the not, and then the CNF right here, right? I could say, like, okay, we'll just recursively apply the CNF rule to the formula itself, right? I could imagine saying do this, but this doesn't work. Let me show you why this doesn't work. Say this is a CNF formula. So this can be a bunch of clauses ANDed together, right? If I take all of that and put it inside of a not, then the total thing here is no longer a CNF formula. So we can't do that. So instead what we're going to do is, it turns out this is easier if we start to break it down by what's inside that formula. Now, what can be inside that formula? If it's another not, right? If we see not, and then some formula, well, that's much easier to say what we can do. That'll be equivalent to the CNF of the formula itself, right? Right, so now this is a CNF, right? So this, it works. I can say, okay, if you see a not and then a formula, ignore the rest of, like, we'll figure out what to do with the rest of the formula here. But what you can do with those two nots is just eliminate them. And then if this produces a CNF, then this is producing a CNF. So what we have to do at each step is maintain the equivalence of the formulas and make sure that the right-hand side creates a CNF. The left-hand side is always going to be CNF and then some free SAT formula here. The right-hand side has to be a CNF somehow. And so I can't do things like put a not on a CNF. This is a CNF because we're building the CNF function to generate CNF. So if we build the whole thing right, then this will work. Right? It's kind of that recursive function design process. Okay. So we continue. We say, what if what came in was a not? And remember, we're looking at what to do with not and then a formula after it, but we're breaking that up into its cases. So if this is a formula and then another formula, I'll use this symbol for the other formula, right? So if that is the input to the not, what can we do? Well, we could run De Morgan's law and turn this into the CNF of De Morgan's law says we do the not of this formula or the not of this formula, right? So we build a new formula inside the CNF space that runs De Morgan's law. Now, is this progress, right? Or did we just kick the can down the road? Well, it's going to be progress if we can figure out a way to deal with or expressions. Because now we have an or expression at the top instead of a not expression at the top. So if we have plans that deal with ors later on, then this is a solution. But if it turns out that when we get to an or, our only solution is to kick the can down the road again and like do De Morgan's law again, then it's not progress. Okay? So we're going to defer that and maybe put a little star here, like pay attention, did we actually make progress? But that's our plan for now, is to kick the can down the road. Now, if this doesn't work, we'll come back and think of a different thing we could do, right? And we might be able to say, like, wait, is this already guaranteed to be a CNF if I do, like, the or of these two things? But the problem is if I have a CNF or another CNF, that's not necessarily a CNF, right? If I have two CNF formulas, I can AND them together, and I get a CNF. But I can't do anything else with them. I can't take a CNF and not it. I can't take a CNF and OR it with something else. I can only take a CNF and then use AND to combine it with another CNF, and that preserves its CNF-ness. But there's no way to export this outside of the system, right? So now let's look at what happens in the third case. So we're doing what happens when we deal with not, and we have an OR underneath the not. Well, we can run De Morgan's law and turn that into an AND. Right, so that would be equal to this. Not this and not this. Whoops. And here we can actually make progress, right? We can make additional progress. We can say, oh, well, in that case, what we're really saying is we're going to split this into two separate CNF conversions, finally. We're going to have the conversion of the not of this formula and separately the conversion of the not of this formula. Again, I was just explaining this. We can actually do this now. We know these are equivalent. How do we know that this is equivalent with this? Well, what I'm basically saying is the CNF conversion of this is equivalent to this. And what I'm doing here is saying, well, give me the CNF of this half of the AND. Give me the CNF of this half of the AND. So this here is equivalent to this here. This here is equivalent to this here. So if I have four things, right? I have this and this. That's 2, 3, and 4. I have 4 things. This pair is equivalent. This pair is equivalent. Then I can make another equivalent of this whole thing here with this whole thing here. Those are equivalent. Why? Because I've grabbed the equivalents of these and the equivalents of these are then both, factored through this AND together. So this whole thing is equivalent to something where this is ANDed with this. This whole thing is equivalent to something where this is ANDed with this. And since each of those constituent parts line up and are equivalent to each other, we have equivalence of the whole picture. So that's equivalent, and it's a CNF. So here you can see we made progress. If we have a knot with an OR underneath it, then we take the knot of each of the independent pieces and put those through the CNF conversions, and then we AND together those results, and that makes a CNF. Okay, so there's some amount of progress here. Now this here highlights the fact of a more general rule. While we will probably want to be able to do this in one step in our rewriter, the general rule here is if I have a formula that has an AND at top, then that's pretty easy to deal with. That is going to go through the same logic. The knots here make it a little bit more complicated looking, but it's just the same logic. We have something equivalent to the formula on the left-hand side, ANDed with something equivalent to the formula on the right-hand side. Cool. By the way, does this have like, I always wondered, nah, it's a little sad. I should see if there's an update to Milton so I can make it go full screen while I'm doing this, so I can like hide the tops and bottoms, make the screen perfectly just the canvas. But it's fine. Anyway, so that's the rule for AND. We didn't have to break it down into cases or anything. Nice and simple, that's how we deal with AND. So the only problem we have is we haven't got a rule for ORs yet, and we maybe kicked the can down the road. So maybe ORs are going to be complicated, just the way knots were complicated, and then this wouldn't work out. Let's take a look. So if I have an OR of two formulas, how will I rewrite that? We know we can't do this trick again, because even though we could put the OR there and make it equivalent, the OR there wouldn't make it a CNF. And the thing on the right has to be a CNF, so we can't OR together two CNFs. But we need something to do here, right? So we need a solution. We could try to play with De Morgan's law and say, like, well, what if I put a couple of negations on this formula here, and then I moved one of them in, right? Moving one of them in putting two negations on it makes it the same as what it originally was. Moving one of the two inside the parentheses converts the OR into an AND. And so you could imagine if you did that maybe you've made progress because now you can apply the AND rule. But we would first have to peel off the knot, and we would find out that when we have a knot with an OR underneath it, we put it through this rule here. So knot, parentheses, Let's chase that down and see where that goes. That might work. Not. Like this. Which can then be rewritten again. Right now we're just rewriting the formula underneath the CNF in equivalent forms. Not this, and not this, right? And so if we go that far, have we made progress? Well, the not and rule says to rewrite it into an OR by De Morgan's law. So if we were to do that, we would get this or this, which just takes us back to the beginning. Right? So since we, like I said earlier when we put this down, if we use De Morgan's law to kick the can down the road here, then we're not going to be able to get away with doing it again here, because that's just going to flip us back to where we started. De Morgan's law is like a switch. You can flip it back and forth. But if that's your only move, then both sides of the problem are just kicking the can down the road. So what I think we want to do is we want to think of, if this is an OR, let's break it down into smaller cases and see if there's a way that it becomes simpler to deal with. If we have, let's switch colors here to explore. If we have a couple of variables, x0 or x1 as our input, that's already a CNF, right? So if this was already a CNF, we wouldn't have a problem. The part where it becomes interesting is, what if there are formulas underneath that? So what if we want to have, well, let's talk about this. We are not allowed to write an OR between two CNFs, but let's see what would happen if we did. Say we have a CNF here. How do I want to write this down? So a CNF is like an OR, an AND of ORs like this. So here's our first CNF, and we want to make an OR out of another CNF. Could we somehow rewrite this into a CNF, right? How could we do it? If we had two CNFs and we wanted to OR them together, how could we OR them together and make them a CNF again? Well, there is a distribution property, right? So we could go over all of the ands, or all of the clauses here, and all of the clauses here pairwise, right? This would be like foiling. So pairwise, we would then get that this ORs with this. So let me use a different syntax here. So we have clause 1 and clause 2 ORed together, clause 3 and clause 4, right? So these are clauses. By clause, I mean they're one or more variables ORed together underneath, right? It's not a variable, it's a clause of a CNF. So it's an OR with possibly multiple variables, right? And so this is a CNF and this is a CNF, but the whole thing is not. Now the question is, since this is just a general SAT again, can we make an equivalent thing out of this that is a CNF? And what I'm saying is we could do a FOIL, right? We could do C1 or C3 and C1 or C4 and C2 or C3 and C2 or C4, right? So this is like the FOIL. Let me try to write that in a way that's a little bit nicer looking. FOIL. Right, so there we go. This is like the FOIL from there to there. This takes in two CNF formula and ORs and combines them by OR and rewrites to a CNF formula by FOIL. Or more generally by distribution. Right? FOIL is just a fancy way to distribute a 2 by 2, but these could be CNF with lots of clauses, and so we would end up doing a walk over all the pairs of clauses across the OR, right? So C1 and C3, C1 and C4, C2 and C3, C3 and C4, C2 and C4. If we had like 10 and 10, then we would generate 100 of these, right? So it's like an n times k expansions of the size. So Wizard of Datums. I'm happy to have inspired. What part of this are you going to be reading and learning about? I'm curious. Um, so let's come up with a symbol for this operation. I'm going to call this the CNF OR operation. And so then this isn't an OR of two CNFs, but it's the CNF OR of the CNF of the first formula all the words. All right. Do you want me to give you a couple of primers of where to look? I won't give you the full lesson, but I can give you if there are words. Not knowing terminology can be hard to use. It can be hard to track down unknown terminology. So I'm happy to give you some keywords to look for. Right, so here I'm doing the CNF OR of, whoops, I didn't mean to make that an and, that's not right. That should be a comma. The CNF OR, actually let's do that comma in green, that seems more appropriate, since it is a comma separating things at that level. So the CNF OR of this CNF and this CNF. So the output of the CNF OR is a CNF. It has the logical equivalent of an OR. So it satisfies both of the needs for a rewrite here. And so then we get a CNF from this and a CNF from this. And we now have a rule for rewriting everything, right? We have a rule for rewriting variables, which we can see. We just rewrite them as variables. We have a rule for rewriting negation, and we do that by looking one layer deeper. So double negation goes away. Negation of an and will be turned into an or, which we now know is actually going to mean that we use the CNF OR. We use the CNF OR of CNF on the first one. Comma, the CNF of the second one. Boom. Boom. Right? So now everything we have here has a full rewrite into something that is equivalent and a CNF. We have input, a general formula of some shape. We break it down, and then we take the pieces that we didn't break down and pass them in recursively to the CNF breakdown system. And so that right there should take any formula to a CNF formula if we convert that into executable code instead of just a sort of symbolic representation. Later, Rizoma. All right, so terminology guide. What you're gonna want to look up. There's a few things. So SAT. If you look up SAT by itself, there's some problems because it also is it is spelled in the same way as this SAT test thing that's out there. So if you don't want to end up getting an SAT study guide, you want to type SAT solver or SAT problem or Boolean SAT satisfiability. These things will give you better results. SAT Solver will give you code people have written that actually implements these. If you look up Boolean satisfiability, or just satisfiability problem, or SAT problem, something like that, you'll get information on what the SAT problem is. If you then look up SAT problem CNF, you'll get the terminology for what that is. That's conjunctive normal form. Um, and you figure out like it'll be those will be the things. So if you look up SAT conjunctive normal form, let me use my text editor. I don't want to spell that by hand with my typing, or I'd rather use my typing than my handwriting for this. Conjunctive normal form, right? CNF. This is a you'll in the realm of Boolean stuff, you'll find out that a conjunction means and, right? So once you understand the idea of and or gates, conjunction is a overly pedantic word of saying this. Conjunctive normal form could be called and, like normalized and form, right? You could call it something like that. And it just means that you have a bunch of things anded together, and that those things are just ors, right? So that's what you'll get there. You'll learn about that. If you look at solvers and stuff, they'll just all reference this. Excellent. Yes, ChatGPT probably can give you good terms here. Now, there's a couple of different of these conversions. We're currently doing the naive conversion from SAT to CNF-SAT. We're also going to do the Satan transform. I'm never sure how to pronounce. I'm never sure how to pronounce it when I start trying to say it. But the spelling, I'll just use the internet to pull this up. It looks like this. This is what we're going to be doing in a little bit later. So let me give you a minute to catch that. That if ChatGPT might lead you to this too. That's going to be a little bit different from what we're currently doing. But it kind of builds on top of what we're doing. So knowing the naive conversion will help a little bit in understanding that one. Okay. So we could build this, and it might be worthwhile to do. I'm gonna go back to the coding now. And while you're looking at SAT solvers, the other side of it is oh, you played Turing Complete? That game is so cool. I love that game. Yeah, so SAT is going to be in a different direction. It uses the concept of logic gates, but in a very like mathematical, almost like interlocking logic. It's more like Sudoku or a Rubik's Cube than a computer. But it's still pretty cool. But yeah, Turing Complete, I don't know how far you got into it, like any game that teaches you how to build a computer logically is, I think, a pretty good games in that space are very interesting. Okay, so let me show you guys what the big problem is here. If we were to, remember earlier we looked at if I run my program, I guess I turned off here, I'm going to rearrange my desk for a moment so I can use keyboard instead of the tablet. If we look at the test program here, we turn on the thing which logs the constraints. So if you recall, here at the bottom, it took like 49,000 lines to dump out our entire set of constraints. And that's not 49,000 gates, but it's not much less than that, right? Like this right here is an OR followed by 9 variables. That stands for 8 gates, right? So while there are 10 lines here, 8 of them are gates. This right here is 4 lines that stands for 2 gates. So we're not talking about, and there's a bunch of gates that are hidden as well because the and here is like 1, let's see, let's start from, okay, so skipping this one, it's 1, 2, 3, 4, 5, 6, 7, right? So each of these 4 things is a AND gate above it that is hidden. So even though our count isn't exact here, 49,000 isn't exact, we're probably talking about somewhere around 40,000 actual gates in this whole thing. And anywhere where we have something like this, so not and, remember, not and is one of those cases that's going to go to this line here, right? Not and becomes not this or not this, which becomes the CNF or over here. And every time something goes into CNF or, if these are anything bigger than variables, we start getting explosion in size. So here we would just get this becomes an or, so we'd have this and, well, not and this is the same as anding with not this or not this, right? So this whole formula might just turn into a CNF just by applying De Morgan's law to the not ands here. And in that case, we would not get an explosion in size for this particular problem, right? We would end up with about the same exact thing. Safe save. I don't remember the names of the levels, but yeah, if you play, I tapped out. So that game goes you up to the point where you've built a computer, and then it has some levels where you program it, and I didn't really play any of those because at that point it was more like a crappy programming game than a logic circuit game. And not that that's bad. It's, if you're going to build a programming game on top of a logic circuit game, you're biting off quite a lot there. And I think it's cool to show the ability of, like, you've seen how the physical bits sort of imaginarily lay out in relation to each other, and then you start controlling them by programming them, and you can see them changing. You can actually see the computer doing your code, which is what's cool. But I think that game, at least when I played it, which was more than a year ago now, so it's an older version I played, but I would recommend getting at least the part where you've built a computer. That was how much I played it, and it's really cool. It does start to, like, when you get into doing adders and stuff, it does start to demand pretty deep thinking. Or at one point I went and, like, looked up how fast adders work because I wanted to build a fast adder with the game. It was one of the achievements to build your adder so it could go that fast, like go so that it would run faster. And that was not something I could really handle without spending some time studying how it's done. I couldn't come up with it off the top of my head. But anyway, where this can get more complicated is, imagine these start getting richer, right? So if I had a not and then this was not just an x0 and an x1, but a whole expression of its own, right? Like this could be something like an or a not again, right? Something that cannot just be reduced, but is itself an expression somehow. If these start getting rich, if this was rich and this was rich, then the conversion doesn't just become not this or not this. It becomes this multiplied out thing. So depending on how rich they are, this expands to something that is the richness of this times the richness of this, right? And if that then starts compounding, like if you have one of those happen, so you get like 6 times 5, you get 30. It's like, okay, it's getting a little big. Well, what happens when the next level comes up? It's like, oh, that got combined again in another CNF or with another 5, and so it's 150. And you start having these things where it's like we have these chunks of like 3s and 5s and 7s multiplying with each other, and as you multiply those numbers together, you are essentially creating an exponential growth of the size of the output. So, while this does solve the problem, in the technical sense, Okay. I say we go and implement this, even though it's got this big downside and it might not be the one we want to use all the time. But the reason I say we implement it is because I think it'll work on the Sudoku case without a downside. I don't think the downside will come into play in this particular problem. So it'll let us test out that we've got the basic details there mostly right. One other thing I should do, which I haven't done, is whenever I create a variable, I should make sure to track the max variable in the builder. Okay. Now, how do we build the CNF formula? We're going to want a recursive function that does not allocate a separate formula over and over again, but instead collects up the result into a formula. So it'll pass this through as an output that it's gathering into. And then I think it will just take one of these as a constraint, or like yeah, pass those through like that. Okay. Now, looking at our map here, we want to break this down into cases. And these are the cases that we have at the top level. So the variable case, so some of these are a little tricky. The variable case here, the not case, sometimes we want to be able to subsume a CNF into the CNF without it becoming a separate clause. So I'm not quite sure how that should look yet. When we do something like this, we want to construct two clauses and then combine them into a clause. So this isn't quite as simple as just a gather. It is a gather in some sense, but it's almost like it's got to be a recursive walk of this structure. The baker asks, do you have a use case that you need this solver for, or are you doing it mostly as a learning thing? I have some, it's not quite clearly either one. It's definitely a learning thing, at least half the way. I don't have a use case that's like, I am specifically building a SAT solver to plug it in here because SAT solvers are known to solve this problem and I need to solve it or anything like that. But it's more like I have a series of ideas of how I would like to play with one, and I'm finding I don't have very good interfaces to them in the free open source SAT solvers that I can find. So my use case is that I want to play with one more on a like from time to time, and I need a good option for being able to do that is like interfaces well with other stuff that I do regularly, and that is a more abstract kind of idea of a use case, but that's my use case. I just want one sitting around that fits in with how I do stuff nicely that I can play with. And another use case is I think other folks probably would find that they're fun to play with too if they could access them. And there's like the handmade community type folks who like things like a single header library, a nice simple interface, easy to integrate, not set aside as a giant mega program of its own that you work through the command line with, but a small library that you can play with and integrate into different kinds of code projects you're doing. And I don't find anything like that. So I'd like to have something like a STB style single header C library of SAT solver, and that doesn't exist. So that's kind of part of it too. Is just like a part of the use cases I think other people probably could benefit or at least learn more about this topic if there was an interface to it that that worked inside the context of something like the handmade community ethos, approach to programming, all that. So anyway, let me think about how to do this. If I am walking along so I need to be able to call the CNF inside of itself and do something with that. So select CNF. Yeah, we need something like what is this? This is naive, the naive context. Okay. And what we'll do is we'll say, when we set one of these up, we create the naive context. The naive context knows the formula pointer. It can't carry the arena with it. That needs to be explicitly parameterized in case that's a scratch higher up the chain. But then what we'll do is we'll say, instead of passing through and out like that, we'll pass through a context like this. And hopefully that'll help us organize this. I don't know if it will, but it felt like it might be the right way to approach it. And then, so the way you would do this is you go arena context and then give it that right there. Now the way you build up a CNF formula is you attach clauses to it. But I think sometimes I might be building a clause without knowing how many literals are going to be in the clause right away. So what we probably need is a loose version of a clause that can look like this. And that just carries, I guess these end up being more like citizens of this section of the code. Fat, sat, lit, so it carries a literal with it. And so we have the literals that we're putting into this clause. The free list of the literal nodes. And what we'll do CNF from con naive, CNF naive recursive, right? So we can have things like helpers if we want, like CNF naive emit clause, finish clause, maybe, and that'll go on to the context like this. Okay, I'm feeling like recursive function land isn't a good idea for this for a couple of reasons. What we want to probably do is have a scratch here. And then instead of having a context, which we are going to end up regretting, I think, we will just make these local properties of the function. So none of this. Here's the formula. We need a set of these things. So this will be lit free, which will be initially empty. This will be lit change will be initially empty. Lit count will be initially empty. And that'll get managed on the scratch. And we're just going to need like a naive stack. Right. And that'll contain everything we need to deal with the recursion locally. Let's look here. Right, and then what we're going to do is we're going to have this be called, well, let's keep the root variable and we'll have a concept of the constraint we're currently dealing with. We're going to want that stack. Along with its own free list. And then we have the main loop of the algorithm, which is going to look at what it's got and switch on it by case. And let's think about this. If it sees a variable, it's going to look and see, are we already building a clause? You know, I never wrote down here what to do if we see a not variable, but that would just be a literal, right? If we see not variable, then this should actually be lit, not var. Let me fix that. So if we see a literal, why can I never do italics for more than the first letter? Then it's a literal, right? So if we see a variable, either it's positive or it's negative thing by itself, which is actually, I mean, another better way to write this would be that there's just another case that I skipped, actually. When we break down not, it should break down into 4 cases. One of them should be not var, and then that can just come out as not var, right? So whenever we do this or this, we're emitting a literal. The emit literal means emit it into the current clause we're building. If we're not building a clause, you summon one up, but you don't actually have to summon one up, you just put it into the chain. If you see, let's look at one of these simpler ones. So if you look at this one, we see an and, then we'll say do this and emit a clause. Whenever we do an and, we emit a clause here, and we do this and we emit a clause, right? That's a whatever. When do we actually know that we've found a clause? We're walking around in these. We go, we're going to do this and. So we would push onto the stack that we need to join to any clauses this makes. So this wouldn't do any. We'd say that CNF would have known to finish its own clause by now. Let's say that. Now say this is a variable. It'll go in there, make a clause. For the variable, but when does it finish the clause? How does it know how to finish the clause? Let's think this through. So this all works. The only problem is I don't want to build the CNF as a tree. I want to build it at a lower level. So I'm trying to think of how to translate this into a low level pattern where I just need to know when to end a clause. Here during CNF OR, it would be pretty easy. We know that we got 2 CNFs in, and so we're ORing together clauses. ORing together 2 clauses creates a clause. Okay, so that's interesting. The final thing will have clauses in it, and we can't emit clauses just because we find them. You know what I'm saying? So like, if I find this clause C1, I don't actually want to emit that into the final problem because I want the C1 doesn't show up in the final result. It shows up as part of this result and this, but it's not its own clause anywhere in the chain. So maybe I've oversimplified the case here. Okay, let's build an intermediate data structure instead. So I was thinking of trying to build this straight into make a formula, but I'm thinking now, let's take a step back. We will want something like that, but let's think of what the intermediate data structure is. We'll just have naive nodes that'll be the Lego brick for this structure. A naive node, let's see, what comes back can be a literal. It can be a literal. It can be a clause, or it can be a formula. Okay, those are the 3 levels. So basically these are just a variable or a negation of a variable. A clause is a list of literals, and a formula is a list of clauses, right? And so these nodes form a simple tree like this. Okay? And when we get back something, we can look at if we got a literal or a clause or a formula to deal with it in different ways. So if I allow myself to think of it that way, then maybe I do want a recursive function for this again. naive node. Maybe we don't need the local stack. And instead what we need is I tell you what arena I'm using to build all of this up. And I tell you what constraint I want you to translate. You translate a constraint to this data structure, and then I do a final pass over that data structure to build the actual CNF formula. Okay? Let's try it that way. So for that, I just give it the Scratch arena, tell it build that thing, build this tree onto Scratch, and build it at root. And then we say, okay, let's implement this. What it's going to do is switch on the kind, not that kind. Ah, you're new to arena style programming. Oops, what am I doing wrong? That's the issue. The macro's messed up. Okay. I don't know if you know this, but I've got a YouTube channel over here, Mr. Forth Programming. You can find it at youtube.com. It doesn't say right here, but at Mr. Forth Programming, right? And I talk about arenas. If you come over here, I've got my base layer. I talk about memory management in this episode. Talks about them a little bit. I've got in my operating system series, we talk about memory at the low level of the operating system right there. And I also have spots like, where is it? 2023. Videos like this where I do upgrades. Maybe it's not that one. Yeah, my upgrades 2022. I do some arena talk there. So there's a couple of videos there on my channel about that talk about memory management, would give you how I do arenas in particular. All right, nil, not relevant. If we see a nil, then something bad has happened. So maybe we will return a nil naive node. Just propagate the badness up the chain. Now, let's make sure we have one of those set together. CNF-SAT naive node nil equals this. If I have yeah, so now I have to start applying the logic from this into the code. So case one, there's a variable, and that means we emit a new node onto that arena, and we set its kind to variable, and we set the literal, well, not kind. Where's the other? Oh, literal. Right. Its kind should be literal, not variable. Naive kind literal, and the literal value is just equal to the variable from this, right? It's not negated. It's just that, right? Okay. So that's how we're doing and. Or variable. Let's do not, since that's the next one in my to-do list, or like my picture here. For not, we need to break it down by the C0. So we have to go switch con C0 kind. We broke that down into smaller pieces. So kind of like we take all this and drop it here. Okay, so if we have a not, and then we look at the not's child, and we find a variable, then we do a literal, except now we're going to negate the literal. So it's the negated version of the literal that we return for the node. Oh yeah, we got to return our nodes. Okay, if we run into a not, then what we do is we just set our node equal to whatever we get when we recurse, skipping over 2 layers there, right? So this is us, this is our child. If I'm a not and it's a not, then they cancel each other out. And so its next child is the thing we're interested in, right? If we have a not of a formula, this is the not of the not, this is the formula that we want to go to next. So whatever the CNF gives us on that formula, right? Let's see. Now we have the and. Now that goes into the CNF or. Let's defer that. We'll do CNF or next, but let's do this one. Actually, no. So both of these are gonna match into this or and land here. Let's do the and the not or after that. So the and in the original bunch needs to look like this. FAT-SAT naive node N1. We now recurse into C0 and C1 in order to make node 0 and node 1. So we have, what is that? That's this thing here and this thing here. And then we want to combine them with an and. Okay. So this is where it gets interesting. How do I and them together? If something is a literal, I need to promote it to a clause. And if it's a clause, I need to promote it to a formula. And then I can chain the formulas together. Or rather, I want to get to the point where these are both formulas, and then I want to rearrange the linked lists within those formulas into a single linked list. So if I go to my naive node, I'm going to do so if I have 2 formulas, right? So say I have 2 formulas. Well, this is silly in a sense because I know this isn't the correct code, but it's just a thinking aid. If I have 2 formulas, then the correct thing to do is going to be to take, we're going to ignore N1. N1 is going to disappear. We're going to join them together into a single node. And we're going to say N0 last, right? Next. So N0 is a list of nodes. The next thing after its last thing needs to be pointed into the first thing of N1, right? So we're joining that together. And then we're setting its last equal to the N1 last, right? So that's the basic idea. Let's pull that out into a little helper here. CNF, FAT-SAT, CNF naive, join nodes, N0, N1. So that just it pulls that out because we're going to want that at a couple different levels, and we need it's a little more complicated than what I give it credit for. So let's get that helper up and running. Oh, and then the other thing that happens here is N0 becomes the actual node we return. So we're destroying N1 and N0, creating a new node using the original memory of N0 plus the linked list data that contained underneath N1, and that becomes the result. Okay, so FAT-SAT CNF naive join nodes. We take in two nodes. We're going to join them and put the result in the first one and destroy the second one. Okay? So the full logic here is if, first of all, let's assert these have to be at the same level. Okay? That's a mistake if we try to join a formula with a clause. And then, if the in-out last does not equal 0, and the in-destroy last does not equal 0, then what we do is the last next becomes the in-destroys first, and the in-out's last itself then jumps to the end of that. Nothing else needs to change. If this does not equal 0, but this does equal 0, so this is a case where, so in the first case here, they're both containing data. If one of them is empty, and it's the first one, then we're just going to copy the information from the second one over, like this. If this is false, then the second one is empty, and then we just leave the first one alone, right? If this one is empty, and this one has data, then since this is the one that gets the output finally, this one gets the output finally. So if it already has all the data, then it's already where it needs to be. So that should do it, except we need to memory 0 struct the one we're going to destroy. So we've kind of borrowed its nodes into a different place, and so it shouldn't have pointers into them as if it's the list that contains them anymore. Only one list should contain these at a time. So we destroyed this one. This one has the linked list there. Now, is there any other, if they're both empty, this would fail. This would put zeros there, which is the right thing to do. If they're both full, it does this, which is the right thing to do. If this one's full and this one's empty, then nothing happens, which is the right thing to do. And if this one's empty and this one's full, then this comes here, we move that there. Yep, all those cases look good to me. So that's how we join nodes. And then we set the result there. Now, the only problem is these might not be at the same level. These could be literals, these could be clauses, these could be formula. So the other thing I want to have is a helper that goes like this. FAT-SAT CNF naive promote to formula N0, N1. So promote to formula will create an equivalent CNF. If I have a node that's a literal, that literal by itself can be thought of as a formula by first saying, well, this literal by itself could be a clause, and this clause by itself could be a formula, right? So it's just moving it up the chain, right? So I'm going to want these promotion helpers down here. They're going to look like this. FAT-SAT naive node, FAT-SAT CNF naive promote to clause. CNF-SAT promote to formula. And the idea is that it's flexible. It'll promote something of a lower status up, but it'll also take something of a higher status and leave it as it is. So I don't have to, when I ask for promote, I just get the promoted version. I don't have to like do all the logical if checking of do I want to change this or not. So in order to promote something to a clause, its kind should be literal, or it could already be a clause, right? These are the things that are allowed. If you try to promote something to a clause and it's already a formula, well, that's a problem because I can't turn a formula into a clause without changing its meaning. But if you give me a literal here, then what I'll do is I'll construct a new one, a new node onto the arena. And that'll be a clause type, and it'll contain the literal constraint, and then that is our promoted version. Now with this one, you're allowed to give it a literal, a clause, or a formula. And first thing we'll do is we'll give it a promotion to a clause. So what that'll do is say, well, yeah. If what we have isn't already a formula, then promote it up to a clause. Which it might have already been, in which case nothing will happen, or it might have been a literal, in which case that does the clause part. And then we can assume this is a clause afterwards. We know for sure it's a clause. So now we just put it into a formula, like that, and return the result. So if it's already a formula, nothing really happens. We set this to the formula, we see that this is already a formula, we leave it alone. If it's not already a formula, we ensure that it's a clause, which may or may not involve constructing the clause, and then we put that clause into a formula and return that. So that's how the promote is working. Then once it's promoted, this if, like I said, is silly, it becomes irrelevant. We don't actually need it. So we get the N0 and N1, make sure they're in formula mode, and then we join them together, and then we return that new formula. Okay. So that's how AND works, and that means that's very similar to how that's going to be very similar to how the not or is going to work, except it's going to get a little bit spicier, right? So not or is going to go like, hey, do the recursive logic on this, and that's not quite right. Why is that not quite right? Because we actually want to negate these. So I could do this in one of a couple of ways. One thing I could do is come up here to the constraint structure and build a constraint around this that is negated, right? I could just say like, oh, we'll make a temporary constraint that negates this one, and then pass that in. And then it would see the not and decode it onto here. Another way I could do it is to say that there are actually like two flavors of this recursive CNF naive function, right? So let's just organize all the naive CNF helpers here like this. Just get them all working together, right? Okay. Is this what nerds do in their free time? Are you talking about the YouTube channel or all of this stuff over here? I am definitely a nerd, but I don't do it in my free time. I mean, I used to do it in my free time. Now I kind of do it full time. I'm not really making money on YouTube, but you know, it's a part of my um, I consider it a part of my business to grow an audience and to raise awareness about various projects I have going on. But yeah, this stuff is totally totally just my way of having fun as a nerd. 100%. Absolutely no excuse to be so indulgent as to build a SAT solver in C for yourself, except that it's fun. So the other way I could do this is I could say, hey, there are two flavors of this recursive function here, right? And what I mean by there are two flavors is you can see that in any place where I'm applying it to a formula. Like here, like I'll underline the ones that don't really count. This one doesn't really count because it's not final. That one doesn't really count because it's not final. But these endpoints, you can see I'm always applying it directly to a formula or to the negation of a formula. So what I could say is there are two flavors of the CNF function. There's the one that takes in a formula and works on it, and there's the one that takes in a formula together with this not, right? So instead of literally saying it always takes in a formula and that I need to modify my formulas when I pass them in, which could be done, that could work, but another way to do it without having to construct this like node data structure thing to get it to do the right thing would be to say that we have a negate option, right? And so when we first call it, we would not negate. And whenever we call it in here, we just ask ourselves if we mean to negate it or not. So we double not, no negate. Okay, here we go, yes, negate that, negate that. So it's not C0, C1. When we do the not of the or, we want to do De Morgan to move the not inside the parentheses, turns it into an and then the not goes on to each of the CNF like recursive passes. So now the negate lives right there, and I don't have to build it as a constraint node. And then I just join them together as an and afterwards, right? So the only issue is I haven't implemented this negate flag to actually do anything. How would that work? Well, it would work the same way as if I just saw a negate node. So what I'm going to do is say do negation cases equals negate, and well, I'm not sure. I'm going to say this is what we do if we do not negate. And maybe I'll figure out how to reduce this down later. But if we do negate, so if we have the negate flag, then it's basically like we're already this far in. Like we start off as if we just decoded a not node and continue from there. Except that it's not going to have that extra C0 on it now. So if I see a variable, I turn it into a negative version of the variable. If I see an or, Right, I gotta be careful. This shouldn't be con C0. So this becomes, okay, I see. Treat negated equals 0. Now, if we started with the negate flag, then the one we're going to treat negated is con. And we won't do this, which is normal. This is fat, sat, con, treat positive, treat negative, okay? And if we have negate, then we're going to flip it around. We're going to treat positive set to 0, treat negative set to con. Now, if we go in here and we treat this as positive, and the first thing we see is a not, then we're going to say treat negative con C0. So all occurrences here of con, I'm going to replace with treat positive. Perfect. Now here, we're going to go treat negative does not equal 0. So if we have something to treat negative, it could happen in one of two ways. The negate flag got set, and so we are treating the first thing as negative. Or we found a not hanging out with a positive, and so we're treating its child as negative. Either way, we get in here, and now con is going to go through treat negative. So you can see it's kind of like the treat positive case, but we're negating this. The or is acting like the and now, and we're passing that 1 through. But then we finish it up like an and. The not is very simple. We take the thing we're treating negative, and we're saying, okay, if we're treating this as negative, and it's a not, then the fact that we're treating it as negative combines with the not, and they cancel each other out. And so all we do is we treat its child as positive. Right? And we handle that by by going into it recursively. So we go back to, all right, treat this one as positive. It'll call into here and go farther, right? All right, so we've done everything except for the or case here and the not and case. And that's because for those we need the CNF or. So let's try to build the CNF or for the or case. To do this, we want to treat both of the children, right? So I treat this one and this one as positive, or sorry, I treat this one as positive. I think that's a mistake. I think over here, it should be saying negation there and negation there. Okay, but here, we're looking at this turns into this. So we've already decoded the or right here. Now we're grabbing the CNF nodes from each of these by treating the children of the or as positive, which is what we want to do. And then we want to put them together in this CNF or logic. So that's something like node equals fat sat CNF naive CNF or N0 N1 arena, right? So that's a helper that we can write that looks like this. It returns a node. It takes in 2 nodes, which it expects to be formula. So this and this are both expected to be formula, and it combines them into a formula and puts it out. So let's look at how it does that. It is now going to build a new formula from scratch. Right, this is the new formula from scratch. And we're going to return it at the end. We're going to do loops. So we're asserting that to get this far, you made sure you gave us formulas and not something lower level. Each of these should be a formula. Okay. Then we'll call this clause 0. That starts at n0's first child. And we also want to loop simultaneously over the second one. So we have a grid here of all the clauses of the first one and all the clauses of the second one. They are two separate things. It's not like a square iteration or a triangle iteration. It's a rectangle iteration. We have clause 0 or we have formula 0 and formula 1 going. Each of them has their own set of clauses. We're looking at all pairs from those two sets. And for each pair from those two sets, what we want to do, we don't want a destructive join here because we have to join them multiple times. So instead, we'll go like this, and we need a new helper that takes in two nodes and outputs a joined version that is sort of not an in-place construction. So new clause is concatenation of clause 0 and clause 1. And then we want to put that new clause into the children of the new formula. Right? Okay. So that right there is the CNF OR. We do need this concatenation helper that sort of non-destructively does that work. So it's going to be similar to this in that it expects these to be a match, but it's not similar in the sense that it's not modifying them directly. It immediately builds a new one with its own allocation by looping over let's see, if this and this are both clauses, then this is just going to be yeah. Let's say they both have to be clauses for this one, because we would do it pretty different if it was two formulas, and it wouldn't make sense if it was two literals. So cat clauses. Each of those gets a new filled in, and then it gets connected to the output clause. First all the things from A, then all the things from B, and then we return it. Okay, so that concatenates our clauses into a new clause, and that's CNF OR. All right, so all of that works, but then we don't have a formula at the end. Let's ignore that and see if there are other build errors first. Promote. I'm gonna rename these to promote 2 just to be safe. These shouldn't be taking in constraints, they should be taking in naive nodes. Promote clause. Okay, now all that's left is we've built this naive node structure. It should ultimately, we can do this just in case. It should ultimately be a formula. Right, so we build it, make sure it's a formula. Then we need to build a formula, like an actual proper CNF formula data structure, which is a little bit tighter than this. So what we have here are these naive nodes, which they're called naive because they're tied in with my implementation of the naive conversion, and they are very loosely structured. They form like a node tree. That makes them easy to build, makes them slow to run algorithms on, and they don't. Also, I'd have to rewrite my algorithms to match this data structure. So now I transform them into the more natural data structure that is already programmed to be solvable. And actually, I think from here we could just use the high-level CNF construction APIs. Okay, one thing I do probably want to do, just to make this a little make this go a little faster is to put the child count on each of these. So I got to go back and carefully look whenever I'm making naive nodes. Okay, if I make a literal, I don't have to do anything because it doesn't have children. This is being made, okay, right here, the result child count needs to go up by 1 each time I do that. The other way I can do that to make it faster is I can go n0 child count times n1 child count. Here I make a clause, so it should have a child count of 1. And right here I make a formula, so it should have a child count of 1. Right here I'm joining two nodes together. So the final child count should just include the sum of the two. And here, the final child count is again just the sum of the two. Okay. So I get the child counts as I'm constructing things, and then when I'm going to use them to build the formula, that's going to help. Now the next thing, you can see right here I have a way to create a clause by putting data in, but it's through what do I want to call it, a variadic argument. But in this case, I won't know statically how many variables I'm passing because that's actually dynamic. So what I actually want is one where I can pass in an array of literals to make a clause. Here's the formula. Here are the literals, and here's the count. Well, I'm thinking about it, and this isn't going to help either. So what I'm probably going to do is I'm going to change my mind. I'm going to say I don't want to use the high-level API for this. The high-level API just isn't that mature, and it doesn't help. So instead, we'll just build right on top of the arena, the data structure. Maybe in the future I will have a more mature constructor for CNF formulas, but right now I don't have that, so it doesn't make sense to push for it. But what I can do is I can say, okay, the clause count here is going to be equal to the root child count. The variable count here is going to be based on the builder. Remember the builder from earlier? I gave it that max variable. So one more than whatever the maximum variable is, that's how many total variables we have, because 0 counts as a variable. And then the rest comes from walking the naive nodes of the root. Those form the clauses. Call that the clause node iterator there. That way we can then do, okay, make me a clause on the arena. Also make me an array of literals on the arena. We grab the child count. That tells us how many literals are going to be in the clause. As we fill out the clause, we go set the literals, set the literal count, set the max variable. All right, so what we're doing here is we've allocated the clause information. We're going to want to loop over the naive nodes that make up the literals underneath the clause. And we're going to want to write each one of those. So we want a literal right putter. Start right there. That'll be incrementing along with the node itself. And that gets the literal out of each node. Then we'll also do get the variable var from lit by looking at this. We get the variable and we set the, we're going to keep track of the max variable. So that we can put that in the clause while we're building it. All right, so that bakes the loose CNF structure that we got here, called the naive node tree, into a formula. And when you notice, that all goes on the main arena, whereas the naive node tree went on Scratch. So the naive node tree disappears afterwards. And finally, we can return the formula. Although, one thing we haven't done yet, we've got the clause, we filled it. We want to attach the clause to the formula. Like that. So each clause has an array of literals, which gets filled right here, has a max variable, and the formula is made up of all of these clauses linked together. That should do the trick. That should make a formula for us out of our out of our input here. I'm going to turn off the solver for now so that we don't actually have to sit around waiting for the solver to run, because that might take a while, I'm not sure. But we run, we get the tree. It did complete. Oh, it segfaulted. Good, okay. That's fine. What I want to see then is, do I have down here some kind of I want some kind of way to log the formula after it's been constructed. Here it is. Okay, if it worked, this one's going to go away. That's an old way to build the formula. Convert to a CNF formula, log the CNF formula. But I believe we're probably seg faulting before we ever get a chance to get that far, based on the fact that we seg faulted last time, right? So it looks like we probably finished with logging the... We either finished or we're very close to finishing logging the tree itself. It's in the right line area at least. Let's see what remedy says. Yes, this is during the promotion function, which is a recursive function here. The assert is failing. We've got a nil naive kind here. Did we get a nil here? Did we get a nil here? No, but we got a nil. Oh, I know what it is. We didn't quite finish building the naive recursive function, right? We left this blank. Why did we leave that blank? Well, that is the not and case. And so we were just finishing up the or case, which gave us CNF or. The not and case turns into another CNF or, this time with the negates underneath. So we grab what we do for the or case. We do the same thing, but we negate those two parts. That's how we do a negative and. So I have an idea. What if I just did treat negative here? I'm trying to think now, how can I simplify this? So this could always be the one we do. We're always doing this path, so treat positive just becomes con, like that. And then what we're doing is we're saying, anywhere where we would do it slightly differently for the negative case, we will put the difference up there deeper in so that we don't have to use duplication of most of it in order to get the similarity of structure. Now, and an or are a little more interesting, but if we get a not, then what we do is we just say recursively apply this and do the opposite of whatever we were doing. So if con was a not, then, and we were treating it positively, then look at the child of con and treat it negatively. If it's also a not, so that treat negative will just flip back and forth, positive, negative, until it finds something that's not a not, and it'll do the right thing with it based on how many knots it ate up there. Now the two interesting ones are and or. This is the logic of and, this is the logic of or, but if we're treating it negatively, right, so this is where it differs is right here. So first of all, we pass treat negative down unperturbed here and unperturbed here. If we're treating and negatively, then if we're treating and negatively, then we do the CNF or on the N0 and the N1. Otherwise, we just do the regular join on the N0 and the N1. And so or, we do all of that the same way. The only difference is that if we're treating or negatively, then we handle it like this. If we're treating or positively, then we do the CNF or. So CNF when we're doing, why don't I flip these? So if it's not negative, then it's positive. No, that's not less confusing. Okay. If and is negative, we do CNF or. If and is positive, we join. if OR is negative, we join. If OR is positive, we do CNF OR. And so the treat negative goes away. Now we could probably get rid of the recursive function entirely and just do a stack at this point, because we're pretty close now to a understanding here that is highly reapplicable, right? This has two tasks have to be put on the stack to branch here and here, like to go down twice into the depth of the recursion. But yeah, this makes sense. So the negation operator tells us when to flip the treat negative bit. The treat negative bit tells us to negate literals and passes through to the through De Morgan's law. So if we get a negation here or here, we apply De Morgan's law, and so then the children get the treat negative bit, and if they weren't negative to begin with, like if it was just plain and or plain or, same thing, we just keep it. So either way, you keep the negativity property with you unchanged, and then how you join them depends on whether or not you ended up. If you started with an and under a negation, then it's an or by De Morgan's law, right? And if you started with an and, then it's a regular and. So you're either doing the and logic or the or logic, which is this and this. But you're doing those under both of those. Yep. I think this all fits together and should be good. Did we segfault that time? We didn't segfault, but I don't see the log of the formula. So let's take a look at why that would be. Here's where we're building the formula. Let's take a look at what the naive formula system looks like. So there we go, we got a formula. 11,988 clauses. Okay, so that's what we're dealing with. Now each clause, looks like this clause has 9 children. So these should all be literals. And this is just like, yeah, this is just the clause of the first cell. Very straightforward. That's the first clause. What's the second clause like? So the second clause here has 2 children. And so that is the clause of not allowing 1 and 2 to go into the cell at the same time. So that should look like a negated 0 and then a negate the negation of V0 and the negation of V1, right? If we look at this, can't tell, but if we switch to hex, yeah, so that's negation of 0 and that's negation of 1, right? And if we kept going through the clauses, we'd find a bunch more of these negation pairs. So negation of 0, negation of 2. Yep, that works. Okay. So that's all structured as expected. I think that must probably be working correctly. So we build a formula. Let's switch back off of hex mode here. There we go. Variable count, 728, it says, so 729 variables. That makes sense. It should be a multiple of 9 when we look at it as a count. Okay. When that is done, what does the array of literals look like? Okay, so good. That's what it should look like. Okay, so the formula got a clause. So the question is, we get to the bottom here, and we look at the formula data structure. Next. We get all these 2's everywhere. The 2's, there'll be like 36 of them, so I don't even know if I'll be able to fit it all on my screen trying to see all of them. Yeah, this looks fine to me. This looks like it was correctly structured. So then we come in here to log it. Oh, I see the problem. Let's rewrite that as fprintf to standard out. Okay. So once it's done converting it to CNF, it's this list of clauses with a bunch of literals in it. There we go, formula. So there's the first clause, then we get 36 of these. Yep. There's the second clause. This is for the second cell saying 1, 2, 3, 4, 5, 6, 7, 8, or 9 must appear in the second cell. Then it's pairwise going through and saying we shouldn't have any 2 of these at the same time, and so on and so on and so on. So there we go. It is in fact building our formula. I'm not sure why when I ran it earlier it didn't show me this part, but it looks like it was working after all. Oh, wait, because the log was being printed the wrong way. Cool. So now the question is, what happens if I ask this to solve that? And I might, I'm just gonna let it run with the log for now. I'm gonna put it over here in case this is gonna take all day. Okay. My log system doesn't output stuff in the middle of a run. I don't have a way to like put it into live mode, which is a problem. So I'm thinking that I don't want to let this run to completion because I'm not seeing anything. I can't tell how long it's going to take. But it would be interesting to get some kind of idea of how long it would take. And in order to do that, I would need to get it to send out some kind of logging information. So maybe what I'll do I thought we had log functions built in over here. Did we not do that? No, we didn't do that. let's just have the log we already have go live. It's not showing anything. I don't know if that works. Why does it stop there? Doesn't make a lot of sense. Unless it's not stopping. Oh, I've been eating a cookie since the beginning of the stream, a little bit at a time. Chocolate chip cookie. I'm a bit of an addict to chocolate chip cookies. Yeah, it's not getting hit at all, which is, oh, right. An unfortunate choice of trade-off here means that okay. Okay, it looks like it's just caught in a bad case. Let me see if I can figure out a way to get that log. How do I want to do this? Resolve. Resolve to, there it is. So let's see, it first guessed that X180 would be false. Well, that can't be the first thing it did. Except if I'm seeing the formula here, then it couldn't have done anything else. Propagated, why would it be propagating? One guess shouldn't cause any propagation. At least one guess of false shouldn't cause any propagation. Right, these could cause propagation if x180 was tied with them and it was set to true, but if it's set to false, right, like right here, if you set this to true, then all of these would have to be false right away. But this doesn't make a lot of sense. All right, so I think what we probably want to do is have yeah, let's just say anywhere where I wrote log emit in this file, I'm going to put a breakpoint on it so we can see this whole thing's happening step by step. There's a tiny little baby step towards having our visualizer that actually shows us this. There's a couple different ways to think about a visualizer. One of them would be that it's a visualizer that shows how this algorithm works when it works correctly and makes it easy to understand the algorithm as it's supposed to be understood. The other kind of visualizer I might want is a visualizer that visualizes the state in a way that is useful for developing with it. Okay, so there we've dropped the formula. Then we went drop the formula again because of the fact that it's in the log there. So there's the formula again. And yeah, so its first guess is that 180 should be false. That seems surprising to me. I don't know why it would be doing that. But that's what it does. I can't remember if I put like a random number generator in there to resolve equally likely choices or something. So sooner or later it finds this, and this feels weird. So let's look at what this clause is saying. So it's a clause with two parts. Two literals. And just so we're clear, the guess we made was 180. That's a B4. Okay, so this one does show up here, but it's negated. We set in our model, what did we call that? It's in the CVCL. Okay, I want to look at 180, which is B4. This one got the -1 value. So it got set to false. Guess number when formed. Yep, so that's its guess number. No constraining clause. Okay. So, yeah, we set that to false. So this should not have been considered a critical clause. Yeah, so this is a bug. Isolated free literal index came out 0 when it should not have. Isolated free literal index should only come out 0 if eval itself comes out 0. So CDCL eval clause. Let's see here. Yeah, we're only interested in that if the total value is equal to 0. If the total value is equal to 0, that means that the clause is not resolved yet because it doesn't have any trues in it to make it true, and it doesn't have all falses to force it to be false. So it has maybe some falses, but not all falses, and no trues at all, meaning that it has unresolved state. And then, because remember, a clause is a bunch of ors, so as long as we get one true, it's good. The clause will be true. So this free literal count equals 1 means how many of those literals are unresolved yet? How many of the literals themselves don't have a value? And one of these is only free if it doesn't have a value, but it's also only isolated if it's in a clause that has not already gone to true. If a clause has a true living in it, and then some falses, and then one free variable, that free variable isn't isolated because true can be, it's isolated when all the other ones are false. So we only get to that when the free count is 1 and we're still unresolved. Let's see how that changes how things run. So we generate a guess. Our guess number is 1. Our variable is b4. We're guessing false. And we get to another guess. So this is totally different now. We're on guess 2, b5, false. Okay. Let it run. Found a conflict. Now let's look at what this looked like. It looks like, yeah, guess value. Oh, awesome. It's doing stuff. So we got this far. It made some guesses. 1, 2, 3, 4, 5, 6, 7, 8. That propagated that this should be true, which then propagated that all of these should be false. Which is not surprising. When we set one of these things to true, we eliminate a bunch of other possibilities. And so then it starts guessing again. When it reaches its conflict, what is the conflict it sees? Oh. Sometimes when you step over a line in remedy from stopped state, it like doesn't do the right thing. Okay, we want to be patient here because if this is going to take a very long time to run, then we won't get the full log for a while. But what I want to see is how it comes to a conflict. So here we go. It comes to a conflict on this pair. So this clause here was one that was saying these can't both be true together. And since they're so spread out, they're not inside the same cell. So this is like someone's tried to put the same number into two different parts of a column or something like that. Maybe two different parts of a box or two different parts of a row. I'm not sure. But when it's done resolving, it makes this the learned clause. I don't know if that's useful, but that's what it did. This part here, we didn't do the way MiniSat does it, and there might be a lot of improvement that can be made to how it learns a clause. The one we used might not be ideal. But yeah, that's what it does for now. So if we look at this, this will be the whole formula. Some easy way we could do this is start pattern matching this. And then that, there we go. So we can see we learned that clause, that monster clause. We backtrack to before 8, which sets all these variables to 0 because we're saying, hey, forget that we did that. And we start guessing again. Now, something I was concerned about with this particular algorithm is that it seemed to me like it was possible with the way it was written to get repeated guesses. We can see it's doing that here. We can see here it led to the same conflict again. I don't know if it led to the same exact learned clause though. So let's take a look at that possibility. Now there are some differences. It did find its way here a little differently, it looks like. Although it looks like the thing it learned is even more awful. It's going to backtrack those, and then it's going to make the same guess again. So yeah, I think that the things I've learned from MiniSat should be applied now, because there's some stuff about this one that I was originally copying that I think I either read it wrong or it was wrong, and we can do better now. We can see eventually it does find a different conflict. This looks like it might be placement of the number 1 in the first row. And so it learned something quite different than what it's learned in the first couple of passes. It starts making its guesses from scratch again, which is frustrating. Yeah. All right, so I would not expect this to complete anytime soon, because it looks like it's not really getting stuck out of its rut. It's conflicting on the same couple of things over and over again. And the learning process is, while it's moving it along somewhat, it's pretty poor. Looks like now it's trying to figure out how to place a 2 in the first row. These are things it should be able to do better. So from here I have a couple of choices. I could work on the CNF solver itself, the CDCL algorithm in my code, so that it would handle this better. Or I could work on the translation some more and make the not naive version of the translation. The cool thing is the naive translation of the Sudoku problem is actually fine. The naive translation of the Sudoku problem didn't grow the problem at all, and so the Sudoku problem is already so close to a CNF problem that it just didn't create a huge issue there, which means I could just focus on like, okay, well, a better translation wouldn't change anything here. I would still be looking at it getting stuck in these ruts. So can I update the logic? And we're not even talking about a better, we're not even talking, when I talk about updating its logic, we're not talking about faster propagation, although we have plans for that. We're talking about better resolution pattern here, and we're talking about better heuristic for choosing guesses. We're talking about a backtrack that makes a little bit more sense. So what's happening with backtrack that I think is probably wrong here is you'll see it's backtracking to before 8, it says. So it sets all these to 0, and then it makes decision level 8 happen again, so it makes a new guess for 8. And what happens at decision level 8 earlier is if we go and we look at guessed value at level 8, 187 is the same thing, right? It's making the same guess. The whole point is it should be backtracking to a point where it's going to make a different guess. If it backtracks, if it chooses a point to backtrack to but doesn't realize it needs to be making a different guess, then it's wasting its time, essentially, is the thought, right? So I should not be having it make this same guess for so long every time it reaches this point in the decision tree, right? Eventually, it looks like it did actually finally use this to make a new guess. But it's not clear to me, oh boy. It's not clear to me that these gigantic learned clauses would be making a huge difference. If we look at the backtrack here, so yeah, we've learned a lot of clauses. Some of them are great. This was what I would consider a good learned clause, but these, I don't see how that helps it at all. It barely changes anything. So we can also, I think we can upgrade the logic for deciding how far to backtrack. Right now it looks like it's making a bunch of guesses and then unrolling all of them and making a bunch of very similar guesses over and over again. And I think we can actually get a little smarter from other stuff we learned in MiniSat where it wouldn't backtrack as far. And the reason that would be good is even though it might ultimately need to backtrack that far, it shouldn't do that every time if it only really needs to backtrack a few guesses to make forward progress. And the way we can choose, the way we learned from MiniSat to choose the backtrack, it makes a lot more sense than I think what this is doing. Basically, because MiniSat used a way of making the resolution clause that walked through the most recent series of propagations from the most recent guess, and then it looks at, as it was walking through that and seeing what it would learn from that, it also was looking at, okay, what are the guesses that have been made directly tied in with this backtrack process that we made through the current tree, whereas what this one does is it kind of just walks freely through its chain of literals over and over and over again, and so it can actually reach back farther, I think. Like, it can end up thinking that it needs to reach back farther. That's my understanding. It's a guess to a certain extent. Look at this. It looks like it actually finished. But there's a lot of zeros there for it to be calling that satisfied. Yeah, that doesn't look good. I don't think it finished correctly. I think it blonked out somehow and did the wrong thing. So it's not only taking too long, but it's also just incorrect, I think. Because it's giving me mostly zeros everywhere here. And yeah, it's saying it's satisfied, which shouldn't be true. It should at least have 81 ones. At the very least, it has to have 81 ones to achieve satisfaction. I think it also needs to fill in some of the negative ones. Maybe all of them. Although it might be able to get away with leaving a few undetermined. Ultimately, this is clearly not correct. Okay, so I think that this is, this has been a 4-hour stream. I've been at this for 4 hours today. I think that's a good amount of progress today. So, recap. We did the ability to build, well, full recap. We wrote down the rules for Sudoku right here. We wrote down the API. We use that to design and implement the API that lets us create constraints freely in a Boolean formula sort of way. So there's our constraint construction API. We wrote the thing that converts that into a CNF formula. And that's what we've gotten done today. So in future iterations, things I need to do are, I need to spend some time with the CDCL solver and make it better. By a lot, it looks like. I need to implement the more advanced CNF generator that uses a different principle than the one we use today. But I will need a better test case for that first, because the SAT formula, or for the SAT formula for Sudoku is too simple to actually bring out the issue in a clear way. So I need a different problem. I need a different problem for that idea. And then we need an API for, once I've filled out my constraints, this is great, but it's an empty Sudoku board, so there's lots of solutions. I would like the ability to then say, hey, here are the constraints that were given to me by a specific Sudoku board. Like, hey, here are the numbers that are already plugged in. The numbers that are already plugged in should be something I can just go in and set some variables to true and then let it solve from there. And in order to do that, I need a place here where I insert that information. So it could be that I build this whole thing, right? And then I attach to it some assumptions or some fixed values for certain variables or something, and that I then put that through a simplification pass right here before, it might be that I want to simplify it right here in the SAT, at the SAT level. And the reason I might do that is so that it can take advantage of simple things like, okay, well, if this is a 1 inside of a list of ORs, then the whole OR is a true, and so that whole piece of the formula can be erased before we ever make a CNF out of it, right? Stuff like that. So I might want the ability to put in my fixed values at this point and simplify the SAT solution, the SAT formula from that. On the other hand, I might want to have the ability to bake them in later so that I can construct the formula and reuse it for lots of Sudoku boards without having to rebuild it. Luckily, the Sudoku one is quite simple to construct, but maybe it gets to a point where this the construction process is just always going to be fast if we use the Satan option. So the cool thing is, yes, this can explode to exponential. This can be exponentially larger, which means the time it takes to build it can be exponential with the size of the input formula, right? But um, the more advanced one, the Satan transformation, that one stays linear. So this would never get so slow, I don't think. So maybe it always makes sense to build it from scratch and bake these in up here. I don't know. Anyway, that's some stuff I need to do in terms of building out features to make this useful as a tool. Another thing to work on is visualizing. So right now I don't have any visualizing. I might want to start, like I've got this log, which is as close to visualizing as it gets. Um, I might want the ability to run the algorithm and have like a visual, like an idea of what visualizations I could use to see what it did. Like run the algorithm iteration for a step, see how it changed the problem, run it for a step, see how it changed the problem, and so on. Um, so so yeah, I'm not quite sure what we'll do next time that I touch SAT, but those are all possibilities. Probably either working on the SAT solver itself or the visualization will be the initial stuff. But we have other things to do on the CNF conversion. We have other things to do on the API stuff. So lots to do on this still, but it's definitely coming together. Thanks for coming to hang out today. If you are new to the stream and you are interested in this project and other stuff I'm working on, MrForth.com is the best place to go to learn about all of it. You can see where I've got old software projects that are open that you can go and check out. You can see stuff that I've put out on YouTube and different types of video projects I've worked on before. You can sign up for my newsletter and you'll get like sort of monthly or semi-monthly updates on projects and stuff that way. So some cool things to check out there. Also running a podcast where I interview cool people, so you can check this out. And besides that, thanks for coming and hanging out. And I will be back probably on Monday. Although I might be doing something special on Monday. So see you guys then. Bye bye.